In this video, we are going to look at activity 2C, which is looking at heating and cooling curves and the phase changes that occur in them. And so in this activity, we have two graphs, graph A and graph B. And so one is showing temperature increasing as energy is added, and then the other is showing temperature decreasing as heat energy is being removed. And so it's always important to first examine a graph and look at what is on each axis. And so of course here we have temperature on the y-axis, and we have some energy on the x-axis. And so here it's labeled energy, here it's labeled heat removed, but we know that heat is a form of energy. So both are essentially showing the same thing, except that in this first graph we have a substance that's being heated up, and in the second graph we have a substance that is cooling down. So that brings us right into the first question, which is which graph shows a heating curve and which shows a cooling curve? And so, of course, heating up would be on graph A. So graph A is the heating curve. So I'm going to put heating here. And graph B, we have something that where the temperature is decreasing. So this is our cooling curve. Okay, and up next it says, what is the freezing point of the substance? And so, there's only one of the graphs where a substance is freezing, but we can identify the freezing point on both graphs. Freezing, just to recap, is when a substance goes from liquid to solid. And so the transition between liquid to solid and solid to liquid is at the same temperature regardless of what direction you're going. So when we're going from liquid to solid, that would be when something is cooling down, and so it is freezing. But then when we go from freezing, when we go from solid to liquid, we call that melting, or fusion is another word for it. And so fusion and freezing occur at the same point on the graph. So the graph that shows freezing would be graph B because the temperature is being decreased. So you can always kind of identify your states of matter on the graph, and I always like to label my graph. So the hottest temperature on the graph we're going to have in our gaseous phase. So I'm going to put gas up here. And then the second part of the graph is going to be our liquid. And then the coldest part of the graph, with the lowest temperature, that's going to be where our solid is. And then these plateaus on the graph, those are where our phase changes are happening. So on this first plateau between our gas and our liquid section of the graph, this is where the phase change is happening, which going from a gas to liquid is called condensation. And so in section B right here, we actually have a mixture of these two phases of matter. So we can kind of discuss what's happening. So this is the transition from gas to liquid, but we want to know what the freezing point is, which is of course the transition between liquid and solid. So we're looking for the part of the graph where a phase change is occurring, and it's going between liquid and solid, and that is at section D here. So this would be where freezing is occurring. And so we just need to look at what temperature that is at to figure out what the freezing point is. So going over all the way to the y-axis, it's freezing at 0 degrees Celsius. The freezing point is 0 degrees Celsius for graph B, 0 degrees Celsius. Now for graph A, we can label the same states of matter on the graph. Our hottest part of the graph is still going to be our gas section. The middle part is going to be liquid. And then the lowest part of the graph is going to be where our solid is. And so even though this graph is not showing something freezing, it would show something melting because we're increasing temperature. So transferring from a solid to a liquid here, this would be the section where the graph is melting. Freezing and melting occur at the same temperature. They occur at the same point, so we can still use this graph to figure out the freezing point. And if we kind of had a mirror image of this graph, it was flipped over, this would indeed be where a substance was freezing as the temperature drops down to 5 degrees, and then it freezes at 5 degrees, and then we have a solid that is still decreasing in temperature, but is already a solid in section A. So the freezing point on this graph is still at section B, and it's at 5 degrees Celsius. So I'll put that in here, 5 degrees Celsius. Next we have what is the boiling point of the substance. So boiling point, to recap, is where we go from liquid to gas. And we sometimes call this vaporization as well. So the transition from liquid to gas, that's going to actually be occurring on graph A because we're increasing in temperature. So our substance starts as a liquid and then it's going to go into the gas phase, and that phase transition is happening in section D of the graph. So we just need to go over to the x-axis and figure out what temperature that's at, and we see that it's at about 15 degrees Celsius. So our boiling point is 15 degrees Celsius. And then we can figure out the same thing from graph B, but instead of going from liquid to gas, we're actually going from gas to liquid. So we know that this substance isn't boiling, it is in fact condensing, but the point of condensation and the point of boiling are the same point temperature-wise on our graph. So the phase change between gas and liquid occurs at section B, and that's at 100 degrees Celsius. So we'll put 100 degrees Celsius here. Then we have what is the melting point of the substance. And so we already said that melting and freezing occur at the same point, the same temperature on the graph. It's just that melting, instead of going from liquid to solid, we are now going from solid to liquid. But it's going to occur at the same exact point as freezing. So we already checked this, 5 degrees Celsius on graph A, right here where it's going from solid to liquid. And then on graph B, it's going to be at 0 degrees Celsius. Next, it says what letter represents the range where the solid is being warmed. So this is a little bit of a tricky question. We need to figure out the section of each graph where there's just a solid, and then we need to only identify the section where a solid is being warmed. So there's only actually one graph where something is being warmed up at all. So in graph B, nothing is being warmed, everything's being cooled. So there is no section of graph B where a solid is being warmed, so I'm just going to put an X there. There's no section of graph B where we have a solid being warmed up. We have a solid being cooled down, but that's not what the question is asking. On graph A, we do have something warming up, so we should have a section where a solid is being warmed. And of course, we've already labeled the section of our graph. This first section, the coldest section of our graph, is where we have our solid, and it is indeed being warmed up. So that would be section A of the graph here. So I'm going to put A there. The next question says, which letter represents the range where a liquid is being warmed? And so once again, graph B isn't showing a heating curve, it's showing a cooling curve. So there is no section of graph B where a liquid is being warmed up, it's all being cooled. But on graph A, we can see that our section where we have our liquid being warmed is section C of our graph. So that's what we'll put here. So number 7, what letter represents the range where a liquid is freezing? So one of the graphs shows freezing, and one of the graphs shows melting. So freezing is when we are going from a warmer temperature to a colder temperature, and freezing is, of course, when we go from a liquid to a solid. So graph A shows going from a solid to a liquid, so that there's not going to be any section where a liquid is freezing on graph A, so we're going to put an X through that. But on graph B, we have a liquid going to a solid, and that's in section D where that phase change is happening. So we can identify that section, section D. Number 8, what letter represents the range where a vapor, and of course a vapor is a gas, where a vapor is being warmed? And so we need to look at the heating curve, because of course the cooling curve is not going to have anything warming up, so we'll put an X through the cooling curve. And then we need to look at our heating curve, and we have our gas, or just our gas, or our vapor up here, and it is indeed being warmed, and that is in section E. So we'll put an E there. Number 9, what letter represents the range where a solid is being cooled? So of course graph A shows a heating curve, nothing is being cooled on graph A, so we'll put an X through that. And then in graph B, we need a solid being cooled down. And so the section where we have just a solid and it's being cooled is section E. So we'll put an E there. Number 10 says, what letter represents the melting of a solid? And so in graph A, we will have melting, because melting is, of course, when we go from solid to liquid. But in graph B, we won't have any melting because we're going from a liquid to a solid. So I'm going to put an X through the graph B section. And on graph A, we need to look at where the solid is being melted. So we're in the process of going from solid to liquid during section B. So that, of course, is where our phase change is happening, section B. Number 11, what letter represents the vaporization of the liquid? So vaporization is where we're going from liquid to gas. And so we need our substance to be heating up to do that, to go from liquid to gas. So that is, of course, shown on graph A. In section D is where we're in the process of going from a liquid into a gas phase. So that's section D. And then on graph B, there is no section where we're going from liquid to gas. We're going from gas to liquid in section B, but that's not what the question's asking, so we will put an X there. Number 12 says, what letter shows a change in potential energy? So potential energy is changing at our plateaus. You can think P for plateau, P for phase change, and P for potential energy. And the reason for this is because temperature is a measure of average kinetic energy. And so if our temperature is going up, then that means that the energy that is being inputted is going into increasing our kinetic energy. But when our temperature stops increasing, we're no longer increasing our kinetic energy, so the energy must be going into causing the phase change to happen. It's going in and increasing the potential energy of our substance. So what letters show a change in potential energy? We're looking for all the plateaus in our graph. So in graph A, we see a potential energy change at B and at D. So I'll put B and D. And in graph B, we see a potential energy change in B here and D here. So B and D in graph B as well. And number 13, which letters show a change in kinetic energy? So wherever our temperature is increasing, that's where our kinetic energy is increasing. So in graph A, I see a change in kinetic energy in section A, section C, and section E. A, C, and E. And then in graph B, I see a kinetic energy change at section A, C, and E as well. Number 14 says, what letter represents condensation? So condensation is, of course, when something goes from a gas to a liquid. So you can think of water condensing from the air onto a sheet of glass or a window. Condensation is from gas to liquid. So only one of the graphs is showing from gas to liquid, and that would be graph B. Graph A is showing a transition from liquid to gas. So there's no condensation shown in graph A, but in graph B, our gas to liquid transition is in section B of our graph. So we'll put B here. Number 15, which letter represents crystallization? So crystallization is just another way of saying freezing. So when something goes from a liquid to a solid, we can sometimes call that crystallization. So graph A is showing a transition from solid to liquid. So there's no liquid to solid, no crystallization in graph A. But graph B shows a transition from liquid to solid, and that is in section D of the graph. 16. Which graph would show vaporization and which would show condensation? So it's asking which graph is showing going from a liquid to a gas, and which graph is showing going from a gas to a liquid. So let's see. So graph A shows liquid to gas, so that would be our vaporization. And graph B shows going from a gas to a liquid, so that is our condensation. Number 17, which graph shows a substance that has a higher heat of fusion, and which one has a lower heat of fusion? And it tells you right here, in case you are unfamiliar with the word fusion, that fusion is the heat required to melt a solid. So whatever graph shows that it has less heat required to melt a solid. And so let's look at the melting temperatures of these substances. Graph A melts at 5 degrees Celsius and graph B melts at 0 degrees Celsius. So the substance shown in graph B has a lower heat of fusion. So let's see, so graph B would be lower, and graph A would have a higher heat of fusion because it melts at a higher temperature. And then 18, which graph shows a substance that has a higher heat of vaporization? And heat of vaporization is the heat required to vaporize a liquid. So we need to look at the boiling points this time. So graph A, the substance vaporizes at 15 degrees Celsius. And graph B, the substance vaporizes at 100 degrees Celsius. So graph B this time would have the higher heat of vaporization, and graph A would have the lower heat of vaporization. And finally, number 19 says, which graph shows a substance whose melting temperature indicates that it has stronger intermolecular forces? And so the stronger the intermolecular forces in an atom, the more energy it's going to take to melt the substance, because the more energy it requires to break those intermolecular forces up and cause something to go from a solid to a liquid or a liquid to a gas. So we're looking for the substance that has the higher melting temperature. So graph A melts at 5 degrees, and graph B, the substance, melts at 0 degrees. So graph A, our substance, would have stronger intermolecular forces. So I'm going to put graph A here.